Thanks for being here. So this talk, it's a little bit different than what I usually do. It's less about the technology and a little bit more about the management of and cultivation of a high-quality engineering team to tackle some problems in this area. But let me just start with something light. So think about it. What's the difference between a cat and a dog? So is it that they number of legs? Is it what kind of ears they have? Is it if they have whiskers or not? Is it the color of their fur? It's none of those things, right? As a human, we don't really even think about it. We just look at these and we know that that's a cat and that's a dog. So the computer vision research community has been trying to solve problems like this for about 40 years now. And I would say for the first 25 years or so, what a lot of people were doing was trying to come up with rules about kind of, what really, if we really think deeply about a cat and a dog or any other kinds of objects, what really is the difference? That never actually worked that well. It's actually really hard to make such rules. After that 25 years, there was about a 10-year span where people were kind of mixing sort of rule-based expert systems with sort of sprinklings of machine learning and gradually adding more and more machine learning, and it worked better. And it's really just been the last 5 years or so that the rise of deep learning, the kind of the most holistic machine learning approach has been applied here with basically no rules, has really cracked this problem. And just to kind of illustrate that, so one of the most widely studied sort of computer vision research challenges is called ImageNet. This shows that from 2010 to 2016, collectively the best result on this benchmark went from 30% error, so 30% of the time a mistake is made, down to 3% error. So that's an order of magnitude improvement. And you can kind of see that elbow in the curve close to the left there, where it drops dramatically from about 30% to 15%. So 2010 and 2011, people didn't use deep neural nets. 2012, people started using deep neural nets, and that was a big improvement. And since then, we've come up with deeper neural networks. We've come up with more clever tricks to make neural networks better. But basically, the rise of deep learning and progress in deep learning has been the biggest driver in computer vision research. And arguably, at least in computer vision, which is the AI application I've spent the most time on, deep neural nets, sort of the last 5 years, probably the most productive era of the entire time people have been studying this. This isn't just about computer vision. You can find similar charts to this from people who do speech and audio understanding work, from people who do NLP and text, from people who do LiDAR and more sophisticated types of, more exotic types of sensors. It's all there. This is the kind of stuff that's motivated us to use deep learning because it works so well. Just an industrial example. So Chris Urmson is the co-founder of a company called Aurora, and he used to lead the group at Google that's now called Waymo. And he basically says, if I paraphrase this long quote, used to be that people would spend endless time writing rules to make things like object detectors, to spot objects on the road. But now if you gather the right kind of data and feed it to an algorithm, which admittedly is still built by an expert, like PhD or similar often, in a matter of a day, you can build something that's as good as what the old expert systems could do. And it's not just about the time to get things done, it's also about the quality of results. So deep neural nets often get better results. It takes far less human overhead, human work to extend deep neural networks to not just new categories of objects, but entirely new applications. So this is pretty exciting. I think this is this kind of advance that's happened in the last few years in AI is probably why a lot of you are here. So an overview of the rest of the talk. So I'm going to start with just a little bit about DeepScale, for those of you who don't know us. I'll sort of motivate, why would we want to build a team of people who work on the full stack of capabilities within deep learning? For completeness, I'll kind of explain at least my view on what is the full stack of things in deep learning. It's more than just designing neural net models, although that's important. There's a whole range of activities that need to go on. And then finally, I'll give some tips and tricks on how to build, nurture, and expand a full stack deep learning team, and at least what kind of things have worked for us. Starting with a little bit about DeepScale. So I started the company about 3 years ago with Kurt Koitzer. Kurt was my PhD advisor at UC Berkeley. Together, we spent a lot of time while I was a graduate student, I finished in 2016, developing very, very low power, very low resource requirement neural networks. So we were able to design brand new nets. SqueezeNet is one that we published. We, of course, have lots of other ones that we haven't published that are able to use less compute resources than anything else. And we also have done work on speeding up training and other aspects of broad problems in deep neural networks. Starting the company, our vision really was, and still is today, that billions of devices will need very small, energy-efficient deep neural networks. There's a lot of stuff where communicating back to the cloud in real time just isn't feasible. And those applications range from the home and consumer applications to vehicles ranging from things as big as semi-trucks and to as small as little drones, and the workplace, ranging from factory, office, construction, warehouse, and so on. There are all kinds of devices, widgets, and gadgets out there that will need very high-quality AI, most likely based on deep neural networks. So this is our kind of grand vision for the company, is to enable this. Although, as I'll get to the next slide, we're about 25 people right now, so we can't do all of this at once. So our favorite application is in the vehicle space. So we make deep neural net-based solutions to help cars, both for driver assistance and full autonomy, to make sense of their surroundings using deep neural networks. Our team today, we've got 25 people total, 18 engineers, of which more than half came from Berkeley, and about a third of those engineers have PhDs. And this will be interesting later when we go into kind of team composition for building these full-stack deep learning teams. So motivation. So why build a full-stack deep learning team? So if we think about sort of from a business perspective, both for big companies as well as for entrepreneurs, deep learning makes some things easier, but it makes other things harder. So traditional software businesses, which have been a cornerstone of Silicon Valley for a long time now, often the biggest challenge starting out a business or starting out a business unit in a big company is to find what we call product market fit, right? So that's what can I build that a reasonable sized market of people or other businesses will actually buy consistently. And the sort of core of the lean startup movement has been around product market fit is the thing you should start with. It's something you should spend most of your time on at the beginning of any new venture or any new corporate project. And the reason I think searching product market fit keeps getting harder is because software has eaten a lot of the world now, and building a new pure non-AI software business is a pretty crowded area. However, given that sort of general traditional software businesses have been around for quite a while now, there's a large supply of decent engineers who you could hire to help build whatever product you figured out you want to build that people will buy. On the other side, on the right, we've got deep learning-enabled businesses, which are kind of the opposite. So from my perspective, you saw that earlier slide with all those applications of deep neural nets, vehicles, home, workplace. I think there's a nearly limitless frontier of market needs for products that traditional software couldn't do, but deep learning can. And we're only starting to figure out what those are. But it's not that hard to come up with an idea for a product and to validate that idea to the level of, yeah, if I could get a deep neural net to do this and package it up, sure, big market would buy that. So the big challenge in deep learning-enabled businesses is a little bit less about searching for product market fit, and it's more about searching for the right engineering talent. Many of the best deep learning engineers, of which there aren't that many yet, already have great jobs. And so it's the frequent conundrum, and I think what actually is the downfall of broad variety of startups in AI and corporate developments in AI is not a lack of good ideas, but a lack of people to implement them. So why is it so hard to hire a deep learning team? What's so hard about this? So on the top left, basically the deep learning talent war is in full swing. So Facebook, Google, Samsung, and Uber have already proven that there's no continent, no city, no research campus, no competitor potentially that they wouldn't set up a satellite office outside of to scoop up some good AI engineers. Silicon Valley, every good deep learning engineer pretty much gets an offer from these places, and they pay a lot, right? So that's the competition in getting these people. There's also a limited supply of these experts. So deep learning really took off only about 5 years ago. And so these days, an old timer in deep learning is someone who's been doing this for 3 or 4 years. There aren't even that many of those. People have been doing this for 20 years. There are very few of those. But an old timer who's been doing this for a few years successfully is incredibly valuable, and there just aren't that many of those. Then, if you start thinking about what I like to call full stack deep learning experts, who think about deep learning at industrial scale, who work on not just models, but also other aspects like data, infrastructure, implementation, these things, if you want someone who knows all that stuff and is good at it, that's an even narrower, smaller talent pool. And then on the bottom right, there's, if you want all of the above, plus those people have actually built products before, good luck, right? Because it just deep learning hasn't been around long enough for people who have had a few go-arounds with trying to build products out of it. So the more detailed you get in what you're looking for, the more you start to go, wow, I'm not going to just be able to put up a job listing and get what I want. I'm really going to have to think strategically about where am I going to find a mix of experts and sort of raw talents that I can train and have a short-term and long-term strategy around building the team from many angles that I need. So I'm going to take a break from this kind of recruiting-centric stuff and talk about what is the full stack in deep learning. What are the things that people need to be able to do? And then I'll circle back towards the end to what we've done at DeepScale that's worked to solve some of these problems. So our approach at DeepScale to full stack deep learning. So I guess full disclosure, the full stack of anything depends on what exactly you're doing. So I'm not trying to say this is a one-size-fits-all. This is merely kind of how we think about the range of activities we do at DeepScale that to create and kind of everything that surrounds our deep neural networks. So the thing that people sort of default to thinking about often is the deep neural net models themselves, which are very important. I personally spent a good chunk of my career developing those. But there's also the data. There's the infrastructure, and there are the applications, each of which, as I'll get to in a minute, are pretty broad, multifaceted categories of activities. So they're all, you're basically limited by whichever of these you're worst at. So you need to take them all seriously. At least that's my experience. So with these also, I'll kind of start out sometimes with what people initially think you need to do, and then I'll go into what you actually need to do. So data, if you're doing autonomous driving, you just drive around and collect some data. What's so hard about that, right? You put some sensors on a car, go collect data, or if you're doing cell phone stuff, get some camera pictures from people, you've got data. Well, there's actually a lot more to it than that. So for most applications of deep neural nets, at least to computer vision and also to speech, text may be a little bit different, there's annotation and curation required for this data. The annotation, this example here is what we call semantic segmentation. So there are different categories like lane lines and cars and road that are being labeled. And somebody has to design to come up with sort of a protocol for what a human who's labeling this should actually do. So for lane lines, for example, is it that there should be one continuous line, and if it's dashed, it's got a property called dashed in the metadata? Or is it that you just draw out each dash? Right? There are endless rules like this. We have a guide for our annotators for each individual task that we do that's at least a double-digit number of pages, sometimes longer. And it's always growing. It's sort of an endless list of things that the annotators and data curation people need to look out for. There's data storage. So as soon as you start getting beyond individual pictures or individual audio samples and doing multi-sensor, the existing data storage formats don't really support that well. And so that's an example of where you end up having to do your own kind of implementation of time-synchronized data storage over multiple sensors. There are lots of reasons why you'd have to think about that. Simulation is also, depending on the application, can be a good source of training data or test data or both. So having a simulation strategy, which could be simulation isn't relevant to my application, is pretty important. And the bottom right, accuracy metrics are something that I think a lot of people just kind of blindly inherit from others. Kind of, well, this is average precision, this is the ROC curve, whatever it might be, and don't really think about what does my application actually need, and how do I measure whether my deep neural nets are doing exactly that. So this is kind of a range, an incomplete list, but more than just the top left, obviously, of things that the data group and any full stack deep learning team need to take seriously. Okay, now models. So what people often gravitate to when they think about deep neural network models is the model structure itself. So is it SqueezeNet or GoogleNet or ResNet or one of these, right? That's certainly important, and I think we've only explored kind of the tip of the iceberg of opportunities for making better designs for models. But there's also a lot more than just models. So there's what we do before and after running the model, the pre-processing, the featurization, the post-processing. Anytime we do a new AI task using a deep neural net, or really any model, we need new objective functions. The objective function is basically how do we tell the model during training that it's made a mistake? And what do we optimize it for? So objective functions are needed if you do a new task. Also, if you're trying to improve your model for an existing task, the objective function is sort of a lever that's often forgotten about to do that. New layer types. So deep neural nets are an incredibly versatile technology. And I think this is another area where we haven't really explored very much as a community yet of the opportunities. So for those of you who have some math experience, if you took the 3 semesters of calculus in high school or college, probably 1,000 pages worth of textbooks, that's all differentiable math. So any of that pretty much could go in a deep neural net, as well as anything that you could potentially compute a derivative of. So there's a huge range of new layer types, shifting, shuffling, all these things. They're just kind of dribbling out at the research community right now. And I think that will pick up a lot of steam. There's quantization and compression, not to be confused with model structure. So model structure is what's my initial design for the net. Quantization and compression is there anything I can do to shrink that down after I've trained it? Then design space exploration is what's my strategy? Might be fully manual, might be automated, might be some mix of searching over all these other 5 things to find the right solution for my problem. So there's a lot goes into models. Infrastructure. So we hear a lot about TensorFlow and Caffe and PyTorch and MXNet as sort of the frameworks that are often the first touch point people have in terms of firing up a software application to get started working with neural nets. But there's actually a lot that goes above and below these that's also very important, which if you're doing any kind of serious development, often you'll need to start customizing and have people who understand them very well. So at the top, you've got visualization and diagnostics tools. So at the top left, how's my model training? The middle, what's actually inside my model? On the right, what are my model's outputs? The frameworks. And then on the left, bottom left, you've got how can I rapidly train these models? Are there things I can do to chain together multiple computers to train them faster? Turns out there are, but it's actually pretty complicated. So that's a whole discipline. And the bottom right is how do I implement the inference side of the models efficiently so they run really fast when I deploy them in a cell phone or a car or whatever my application is. And then finally, you've got applications. So you've got stuff that runs in the data center. On the left, I would say a lot of these things have started to go into mass rollout products. So I think at this point, you really can't make a competitive image search or text search engine without using machine learning, and quite often deep learning is one of the key pieces to that. But on the right, I think at the edge, on embedded devices, on consumer devices, and so forth, those applications are just getting warmed up. I think we're probably a 1% or a tenth of 1% done as a community with getting deep neural nets where we need them on those. And so, when you think about the full stack team, naturally, with whichever of these you're targeting, you need some domain experts who have worked on maybe the non-deep learning version of this before and have quickly gotten up to speed working with the rest of your team on deep learning versions. So, OK, that's a lot of different pieces. How would we go about orchestrating that? So when I look around in the industrial community, I've spent some time in NVIDIA and Microsoft Research and other places like that. And what I see often is you have very high-quality teams doing 1 or 2 or all 4 of these, but they're each in their own silo. And there's this sort of forward propagation of the data people come up with a new data set, but the model people are training on last year's data set. And the infrastructure people are building new neural net frameworks implementations for 2 years ago's model. And the application people have no way to reach the data people to tell them what they actually want to train the model to do. And so this is kind of a breakdown, I would say, of ability to, in an agile way, get things done. And this is how things are in a lot of industrial settings. The research community actually has it in some ways worse. So the people who go to the models conferences and the people who go to the infrastructure conferences, those are different conferences of people who don't actually know each other. So you've still got people, I guess I would count hardware for neural nets under infrastructure, which is a very broad category, at least for me. And so you go to hardware conferences and you find people who are building processors for a 6-year-old neural net that's not used anymore. This happens all the time. So this obviously has some flaws. And the way I've been doing it at DeepScale, or the way we've been doing it, is to kind of break down these silos and put the data models and infrastructure people in the same room. If they don't fit anymore, have multiple teams that each have these 3 aspects to them. And the application people shouldn't be too far away, right? They should have input to this. Our application people are actually a mix of domain experts that work at DeepScale and customers who spend a lot of time with our engineers. So this has really helped us a lot. Now, the next thing is, does anybody want to do one of these? Would you like one? Maybe? So what lessons have I learned that could help you build one of these teams to do your application? So first of all, I would say a job is actually a product. A travel experience is a product. A digital assistant is a product. There are lots of things that you don't necessarily hold and touch that are products. A job is just an experience. It's a thing that you're going to go do for a long time, hopefully. But it's something that if you're looking at jobs, you're a customer of jobs, right? So a successful product achieves product market fit. A successful job achieves job employee fit. So with this in mind, I've been thinking a lot about kind of what's the hierarchy of needs for people in general who are taking jobs, but particularly I've spent time thinking about these in the context of hiring and training AI engineers. So when recruiting for some jobs, you might be able to ignore this hierarchy. You might be able to say, I'm going to give you money and you're going to give me work. But to survive this deep learning talent war, distinguishing yourself in this hierarchy turns out to be pretty important. So let me kind of just give a run through of what these are. So money and financial upside, at minimum, people need to eat. At maximum, they'd like to get rich in many cases, which is great. Doing interesting work. So this is important, I think, for people in a lot of fields. But particularly if you've been doing deep learning since before it was cool, it's probably not because of the money. It's probably because you thought it was fun. So working on problems that continue to advance the state of the art, that continue to push the boundaries of what's possible, that's interesting work. So providing that is something that you can do to differentiate yourself from people who are kind of cranking out a bunch of stuff from last year and kind of tweaking it for your application. Collaborating with an intelligent team. So I look at our team at DeepScale a little bit like a professional sports team, right? Like, and you probably should too, right? These aren't a bunch of hobbyists that we've kind of chained together in some sort of haphazard way. This is supposed to be like a group that can execute on just about anything. And so, you basically want a culture, at least I've found, want a culture of people who come in looking, for, are these people I'm working with, am I going to learn from them? Are they going to learn from me? That's what we want here. Growing your skills. So again, I'm kind of rattling off what we do at DeepScale just because you might be interested. So growing your skills and career, for people who are kind of earlier in their career, we say, look, you could, we get a lot of people who looked at going to Facebook AI research straight out of undergrad, but realized Facebook AI research really doesn't take many people who don't have PhDs. And the jobs that people without PhDs at Facebook AI research do, can be pretty deep in the trenches and not a lot of room for growth necessarily. That varies, but that's kind of the sentiment among our applicants. And so, our view is, well, you could go do a PhD and then join Facebook AI research, or come to DeepScale and we'll train you pretty quickly to be a deep learning expert. Which has been a huge differentiator for those early career people. For late career people, it's you get almost all the flexibility you would get in a pure research environment, but you get to have this impact, right, of making cars not hit things in our case. And then finally, becoming famous, right? So we share the microphone, right? We give the microphone to smart people, let them really shine, which adds some value for a lot of folks. So who exactly are we looking for? So from my perspective, there are a lot of detailed categories, but two of the broadest categories I could think of are experts, which I'm representing with a little PhD diploma, and generalists. So experts doesn't have to be a PhD, but people with a lot of relevant industrial experience. We're still at a point in industrial deep neural network, at least many places are, where a lot of the work is just copied from academic research papers and tweaked a bit. So a lot of the sources of great ideas are people who recently did a PhD, and you can complement them with generalists who maybe early career, maybe mid-career, are very good software engineers, and hopefully in many cases have some product development experience. These folks learn from each other. So how do we deploy our experts? Let's think about this. So I think the tired traditional model is you give the toughest problems to the most senior people. The generalists sort of do the grunt work until they give up and leave. What I think is wired is having the experts be teachers. They maybe do a little bit of, a decent amount of hands-on individual work, but the expert's biggest goal, is actually to train people and coach them through solving the tough problems. As I'll get to the next slide, this actually scales a lot better if growth is something you want in your team. On the right, we've also, inspired. So experts also can just formally teach generalists in the classroom. So at DeepScale, we're internally kicking off something for our own people called DeepScale University. I started the first class for this about 3 or 4 months ago. It's called Topics in Full Stack Deep Learning. Even as a course number, it's DL401. And we're planning to kind of spawn this out into different aspects of the stack having their own classes. And you might wonder, how could you possibly spare your experts time to do this sort of thing? But my experience is the following. So in year one, you might start like this. You've got a couple experts, you've got a bunch of generalists, and maybe you could have gone faster if you had a few more experts, you put the generalists off in the corner somewhere, and you just put the pedal to the metal. But if you're thinking not even long term, but even medium term, by year two, I've personally seen a lot of these generalists become experts, actually a lot faster than they would if they were in a PhD program. And now we've got folks who have been with DeepScale for a year or two who are completely capable and now executing on this of training more generalists and coaching them through tough problems. And so this has been incredibly powerful for us. I think more folks are thinking this way. Facebook has something called Facebook University, so I've heard. And this is starting to catch on. But I think this hopefully will come to be kind of the default view of how to build one of these teams effectively. So I guess I'm getting towards the end of my talk here. So one thing I've noticed is that full stack deep learning teams produce full stack engineers. So this might be that the generalists were learning from an expert in one of our domain areas of the stack. But eventually, a good number of both the experts and the generalists start to get a lot of knowledge about the whole stack in their brain. And when you do that, you get to a point where you can do some really incredible things. For example, instead of going to the weekly team meeting and spending an hour hashing out, well, if I change the data like this and the model like that and the implementation like that, would that work? Instead of doing that, which we still keep doing, if you have it all in your head, you can every 10 milliseconds refresh as you think about that, right? And you can very quickly come to sort of multiplicative improvements across the stack by just sitting down and thinking about it, doing some experiments, and using your individual knowledge, which is really exciting to me. So now I'm pretty much at the end. So wrapping up, if not, some of you probably came in here believing this, but if not, I really strongly believe that deep learning is not just about training models all day, although that's very important. It's an interdisciplinary field. And the stack in this field ranges from models to data to infrastructure to applications. And as you saw, it's sort of a hierarchical stack. So inside each of these things, there are lots of nuanced topics that, depending on what you're doing, you may need some people who are able to work on those. There are tons of opportunities to commercialize deep learning, but relatively few engineers who can bring them to fruition today. So I would say, traditionally, the mission-critical activities of a business unit tend to be focused around engineering and sales. I would say recruiting is at least as important. I expect in the next few years, one of the core tracks of MBA programs, besides marketing, sales, and finance, to be recruiting. This is a professional, sort of A-player, top talent activity, recruiting. It's no longer you kind of work your way up in an organization as a recruiter. This is one of the most important roles in any company trying to do deep learning right now. And so finally, I know it can be a lot to really kind of put your thinking cap on and really focus your time and your resources on building, nurturing, and growing your full stack deep learning team. But I would do it again in a heartbeat, and I think you probably would enjoy doing that as well. Thanks a lot. I think we have, 10 minutes for questions?
Yeah, so again, thank you, Forrest, for the talk. Yeah, so we have about maybe 10 minutes for any Q&A. If anyone has any questions, we do have a microphone, so if anyone wants the microphone for asking their question, please feel free to just wave me down. Does anyone have any initial questions?
Hi. In your experience, what's a good ratio to start with and end up with respect to the experts and the generalists?
I find if you can swing it, 3 to 1's good, 2 to 1 is great. I think you could certainly potentially go higher than that, but you'd have to get some formal management training for your experts, right? So they really can allocate that time to that many different people and projects.
Does anyone else have a question?
You mentioned recruiting. So what are the standard type of questions you'd ask somebody for an interview if you're just starting with a team of deep learning engineers?
Sure. So I guess there's two sets of questions. One is about, I guess we're interviewing them and they're interviewing us, right? So are you kind of asking about their technical skills to evaluate, or just, okay, so technical skills. I think figuring out, first of all, where in this range of things do they have skills? And then, put them in front of the people on our team who are best at that, right? And so if it's infrastructure, we might go into arcane levels of detail about how computer processors work and how you can optimize deep neural net designs and implementations for them. If it's models, we might go all over kind of, walk me through the math of this particular objective function and why it learns. Data, we might go into, how do you think about iteratively curating a data set where you don't want to start out with the humans manually labeling everything, but you want to have kind of a process where the humans do some work, or the computers do some work, humans check it, and so on. Kind of walk me through the runtime improvements of that, given some assumptions. So those are kinds of things. And applications, at least for me, frankly, they're often telling us, right? Because I didn't start out as a domain expert in the field that we're in. I see one there.
Yeah.
Because I think most young people graduate from school is more experts in one of those areas. So I'm just wondering, how long does it take you to train those fresh graduates and become a full stack deep learning expert?
Yeah, so I guess there's two questions to unpack there. So first, if you've got someone straight out of a computer science program, they did amazing in your interviews, you're really excited to work with them, or they're pretty early career and haven't done a deep dive in any of these areas of the stack, how long does it take us to get to the point where they're really pulling their weight and contributing, right? I would say depending on the person, 6 months is not uncommon. It may be within one section of that stack, they're doing one or two of those tiles really well, right? Then there's the second question of how long does it take anyone on the team to really be skilled in all four aspects of the stack. I'd say that depends more on the person. So I would say this for some people happens, and for some people just continue to specialize mainly in one, right? So it's sort of an individual work style in some sense, and what are we motivating people to do? So I didn't really start out optimizing for this. This is something we kind of discovered by accident, that if you put all these people in a room together, they start to kind of learn through osmosis from each other. Sometimes you get people who, after you come in as an expert in one of these and within a few weeks are kind of juggling all four of them over their head. That varies more, I would say. I see one back there.
Hello? When you say you have experts, do you mean that that person expert in all the three domains mentioned there? Data, infra, and models?
Oh, I see. So these I usually think of as those experts at the top. Those experts at the top usually start out being experts in one, like, in the best case, they're the world's greatest living authority on some aspect of that we care about. Published top papers in that area, built some really exciting thing in that area, maybe collaborated with people on other parts of the stack at a previous company or research project. But often, the further down you go in this propagation over time, the people who kind of became experts in sort of iteration 2 and iteration 3 are somewhat more likely to be full stack because they've had all these different mentors, right? Often, as a graduate student, doing a PhD in AI, you have maybe one or two mentors who kind of push you in a very specific direction. You do a very deep dive, and probably learn a lot of things along the way that kind of generalize. But one thing that was unique about or still is unique about UC Berkeley's kind of computer science program or EECS program is we have these interdisciplinary labs that have about 10 professors, and often it's a range of people on the systems side, on the deep learning side, on cloud infrastructure side. That's a unique kind of mecca for people who kind of grow up in full stack thinking. But depending what kind of background they have, you may have some of those experts at the very top who are super specialized and narrow. They broaden a bit, but by the time you're those generalists at the bottom, those 18 people at the bottom, a good chunk of those will be relatively full stack, I would say.
Does anyone else have a question? Okay, well, again, I'm sure, Forrest will be happy to take any private questions on the side. But again, we thank you for your talk. And again, thank you to everyone for coming. Really appreciate your time here and enjoy the rest of the conference. Thank you.
Thanks again.